Hello and welcome to the last lesson in unit number 3, talking about magnetic induction. So today's goal, I want you to be able to tell me what magnetic induction is and how it applies to the world around us. What are the applications that exist for it? So what is magnetic force or magnetic induction? We're looking at, to start with, the magnetic force on a moving charge. So current is the amount of charge passing in any given time. So it's the exact same as it was in the 3U course. But I'm going to give you a little bit of a different formula. I'm just going to talk about the changes. I'm just going to rewrite it here so it looks a little bit more correct. NQ over delta T. Now, the formula you're familiar with is equal to, maybe I'll go this direction here. Your current is equal to Q over T from grade 11. Same formula. All right, same formula. The difference is Q is the charge of an electron. So one charge of electron. I'm running out of room here pretty quick. So that is the charge of an electron. So I'm going to go up. I don't have a margin like you guys. Charge of an electron. And the N is the number of electrons. Number of electrons. All right, so you can see that it's a variation of that formula. So instead of talking about the total charge, we're talking about how much each electron has, and then multiplied by how many electrons we're dealing with. So what we want to talk about then is length of a conductor. The product of velocity and time for a particle to move from point A to point B. So basically all I'm saying here is delta D. So the displacement is velocity times time. Okay, so that's taken from our back to kinematics in grade 11. I'm just going to change the notation here. So I'm going to go L instead of delta D. So the length of the conductor is equal to P delta T. All right, so I'm changing the notation. It's the same formula. So that's the same formula. That's the same formula, just in a bit of a different format. And what then we can, from that, what can we develop then? Well, I know magnetic force from yesterday's lesson was Bill sine theta. So I'm going to maintain my magnetic field strength variable. I'm going to rewrite with the equation or the form that I have up here from the grade 11 course. So the I is going to get replaced with NQ over delta T. L is up there. It's just using our uniform motion for calculating length or displacement. So that's V delta T. And sine theta will remain. So what does that then result in? Well, it results in time canceling out of the equation, and we end up with VNQ V sine theta. Oops, charge is not a vector. There we go, VNQ V sine theta. Now, what I'm interested in, so here we are, interested in only one charge, or only one electron, I should say. So what does that mean? That means I'm just going to let n equal 1, because I'm analyzing one particular electron. So that means the equation then reduces down to B QV sine theta. Okay, so there are, on this page, 3 formulas to add. This last one is one of most interest for us in this particular unit. So we are looking at the magnetic force acting on a moving charge. So an electron passing through a magnetic field. So we've narrowed it down, or we're focused on that single electron and how it works within that magnetic field. So the first example, a proton with a charge of one positive E, so that's the same charge as an electron except positive, has a velocity as stated there. And what it's going to do, it's going to enter a uniform magnetic field. And it's pushed with a force of 7 times 10 to the negative 12 to the right, determine the magnitude and direction of the field. Well, let's just do a straight calculation to start with. So I'm going to find the magnitude of the force first, or find the strength of the magnetic field first. Then we'll talk about direction after. So I changed the order for some reason as I wrote it out here. So what do we know? Well, we know the magnetic force, 7 times 10 to the negative 12. We know the charge of an electron, except it's positive in this case because it's a proton, negative 19. What else do we know? We know a velocity. So the particle is moving, or the proton is moving at a high velocity. B is the unknown. And sine theta, it doesn't state. So this is, I did it similar to how the textbook questions ask it. If it doesn't state an angle, you assume it's perpendicular. Okay. So I'm just going to put a note here. Assumed unless stated. Or unless otherwise stated, I should say. Just the way the textbook is, so I'm just trying to align with that. So if it doesn't give you an angle, you assume that it's at 90 degrees. Okay? So running that through the calculator, we find that the magnetic field strength here is 1.7 Tesla. And that's only a magnitude. We need to find a direction. So how do we find the direction here? Well, free body diagram is where I'm going to go with this. So a proton with a velocity of 2.5 meters per second down. So here is my electron. It is moving with a velocity downward. Uniform magnetic field, it pushes it with a force 7 times 10 to the negative 12 to the right. So there is a force acting in this direction. So using our right-hand rule here, we need to put our palm heading in the direction of the magnetic force. So this is direction of palm. All right. And what we're going to do is we're going to treat that electron or proton's path as the direction of current, because technically your thumb points in the direction of current. True, what is the definition of current? Well, it is the path of electrons. So if I orient my palm in the direction of force, I put my thumb in the direction of that proton, then we find that my fingertips will be pointing into the board. So unfortunately, because you can't see me, you can't see my hands, but palm is in the direction of the force. This is direction of thumb. So if you can orient your hand toward your screen in such a way, you'll see that your field is going into the page. So therefore, fingertips going into page. So down here below for the final conclusion, therefore, magnetic field 1.7 Tesla and into page. And again, that comes from right-hand rule number 3, our motor principle. Okay, and there we are. That is the answer to that particular problem. All right, traveling on our way here. Centripetal magnetic force. A particle that's moving at a constant speed, and particles do that because they don't have engines or jetpacks. So it's moving at a constant speed, experiences a constant magnetic force at 90 degrees. We'll trace a circular path, so similar to an orbiting satellite. So what will happen is a particle anywhere on this circle here will have a tangential velocity. So it will be attempting to head in this direction, but because of the magnetic field lines, if the force, magnetic force, is directed toward the middle here, it will keep the electron from escaping. Okay? So the electron or the charged particle wants to head in this direction. It can't because this magnetic force is holding it into the middle here. Magnetic force. So it's always pulling it toward the middle. So the electron gets stuck. Now, if you're asking what direction is the uniform magnetic field? Uniform magnetic field, we are staring down its direction. So here are my magnetic field lines. All right, I'll use dots to represent them. Okay, so they are coming in and out of the page, or your fingertips are heading in and out of the page. So technically, this magnetic field would extend outside, but I'm not going to worry about drawing all the dots around and outside here. If that particle travels into this magnetic field influence, it will get stuck in this circular path and won't be able to break out. So what is that similar to? So the equation. Well, magnetic force is going to equal centripetal force. So this is very similar to our satellite situation from Unit 2. We're talking about centripetal acceleration here. We have a force that's keeping something in a circular pattern. So what happens with that equation? Well, we know magnetic force is Q V B sine theta. And we know centripetal force, and I'm going to pick mv squared over r. We end up with this relationship. So if you'll notice, both sides have a velocity of the particle, which means our v will cancel on the one side, exponent will be reduced, and we end up with the equation, or with the formula. I'm going to multiply the r up. So we end up with qr b sine theta equals mv. And what we're going to do here, we're going to assume that theta is 90 degrees. Okay, so assume theta equals 90 degrees. Okay, so that's saying that because those field lines that I drew, those are my yellow dots, so all these yellow dots, magnetic fields coming in and out of the board, that the particle is moving perpendicular to them, so we have that angle of 90 degrees. So it means the final formula that you're going to need in this particular section, it's going to look like that. I'm going to leave it in that format so you don't have any fractions, and you can rearrange it as needed. All right, so there we go. So again, those field lines, magnetic field lines, are coming in and out of the board. So if something enters that magnetic field, it is possible for that particle to get captured in the system and not be able to escape. So it's actually rotating in a circle. And we're going to talk about those applications because I'm going to finish this up. Well, maybe I have time to do the next example. There's not a whole lot to it. Determine the velocity of a particle. Again, it's a proton, positively charged electron, moving in a circular path of radius 8 centimeters in a plane perpendicular to a 2 Tesla uniform magnetic field. So here is the path of the particle. Here is my 2 Tesla magnetic field. So we're staring down. Our eyes are in line or parallel to that magnetic field, uniform magnetic field. Those dots represent the lines going in and out of the board. So our particle then is stuck in here and can't escape. And it's stuck in here because of that magnetic force pulling it toward the middle. All right. So we just talked about the formula for this. So we have Q BR equals MV. So what do we know? Well, we know the charge, positive 1.602 times 10 to the negative 19. We know the strength of the magnetic field. That's a 2. Radius is 8 centimeters. Remember, we need to do that in meters. And mass of a proton is the same as the mass of an electron. 9.1 times 10 to the negative 31 kilograms. And our velocity. Solving for our velocity, we get V equals 2.8 times 10 to the 10th meters per second. All right. So if the particle is caught in this situation, so let's say it was traveling at a velocity of 2.8 times 10 to the 10th, and it traveled into the path of this uniform magnetic field, what happened was the uniform magnetic field captured that proton, and it wasn't able to escape. So it gets caught in it, similar to how a satellite gets caught in the gravitational pull of the planet. And that's what we're calculating here. We're just doing calculations to determine what forces are required, or what charge, what velocity is required for that particle to get caught into this particular scenario. All right. I will continue in the next video, the last video for this unit.